Let's look at an example of using the sampling distribution model for a proportion. And it's also a little bit of an experiment for me. I'm going to try and emulate the book style of their step-by-step examples. Not sure if it's going to be a great idea, but I just figured I'd try. So I'm going to take exercise 11, this is from chapter 18. I'm going to modify it. It says that the national freshman to sophomore retention rate for college, the percentage of freshmen who go on to become sophomores, is 70%. Let's assume that. Let's consider, here's the situation. It might seem a tiny bit artificial, but it's really central to what we're leading up to statistically. Let's look at a bunch of different colleges, and let's say they all happen to have freshman classes of exactly 900 students for simplicity. We want to describe what's called the sampling distribution model for the percentage of students expected to return. All that means is that for each of those different colleges, or in other words, for each, we're kind of assuming they're random samples of the entire freshman population of the country. For each of those samples, each college, they're going to have some percent that return. They're not necessarily going to be 70%. There's going to be a lot of randomness there. But they should basically cluster somehow around 70% if this number is accurate, and we're assuming it is. And what we want to talk about, what we want to describe, is basically a histogram of what we would expect all those numbers for the proportions to be. And so that's an example of the sampling distribution model for a percentage. What we're leading up to, just as a preview of what we're leading up to, is a more interesting example where we don't actually know this number, and we actually go ahead and say we take a random sample of 900 students, and then we try to figure out, and that's going to give us some number, and we try to figure out if, say, that gave us 67%. We'd like to figure out what this mystery number is going to be. That's going to be where inferential statistics really gets going, but we're working up to it, and we'll be there soon. Okay, so this is kind of the last step on the way to that. So let's do the think stage. Plan. What do we want to know? Okay, all it says is describe, and in fact, in the textbook version of the problem, it suggests using the 68, 95, 99.7 rule. Okay, so we're going to be describing a distribution, and we expect it to be approximately normal. Okay, and we'll go through exactly why that's going to be the case. Okay, so we're going to look at the mean and the standard deviation, and then we can say some useful things about it based on the 68, 95, 99.7% rule. Okay, so that's the plan. And in particular, the distribution we want, we're trying to describe how likely is it for each of these freshman students to return. Okay, and what we're going to do is we're going to look at, for all the different colleges, it's not really student by student, it's college by college. And so that can be confusing. We're looking for the individual numbers in the distribution are, if we take one college, one block, or one group of 900 students at a time, what's going to be their retention rate, their percentage. Okay, so let me just go ahead and say that explicitly. The distribution is of each college's retention percentage, not the probability for each student. Okay, and this is really, really important because the probability for each student could be very complicated, and we might not have any idea really what the distribution is, the details of the distribution for each student. But the beautiful thing is that if we just check a few conditions, which we're going to check in a minute, then we can verify that since this is for a sampling distribution for a proportion, it's going to be modeled very closely by a normal distribution. The reason for that is that as long as I have any kind of random process, no matter what it is, as long as I know the general percentage of the probability, here's the 70% probability, if I sample that many, many times, I'm doing a binomial probability calculation. And binomial probability calculations with large numbers become normal. So it really ties into Chapter 17. It's really Chapter 17. The math is exactly Chapter 17 in disguise in the first part of Chapter 18. It's just in a very, very important new situation where we're looking at it kind of more realistically, not as an artificial probability problem, but as a realistic problem that we would get. Okay, so we need to check the conditions. Okay, so the conditions that let us use the normal model, the big one is the randomization condition, and that's kind of dubious here. Okay, we will treat each college, or each college's freshman class, really, as a simple random sample of all U.S. college freshmen. Okay, freshmen. Or first-year students, let's say, not to be sexist. Okay, ooh, that's for later. Okay, and that's kind of dubious, but we kind of have to do that to use the methods that we want. Okay, so we might say, come back to that at the end and say, I don't know if that was really true, because maybe some college only takes a certain kind of student, like really good students, or ones that are really likely to drop out, or ones from certain socioeconomic status or certain regions of the country. So this is pretty dubious, but that's what we have to run with. Okay, there's some numerical conditions that we have to check. There's one which is kind of dorky. Very rarely is going to be a problem for us. The 10% condition. This is the weird one. It's easy to check. It's the weird one. It says we're not sampling too much. Okay, of the whole population. And this is the tricky one. You have to look at, where did this original probability or this original percentage come from? The 70% was the percentage of all, the nationals, the key thing, of all freshmen going to sophomores. They're all retention rate. No matter how many colleges I sample, unless I sample a heck of a lot of colleges, I'm probably not going to be looking at more than 10%. And in particular, this 900 student, each time you sample the 900 students, it's not like you're using up a large proportion of the pool of national freshmen. Okay, so that's satisfied since the sample size, 900, is much less than 0.1 times total number of U.S. freshmen. Okay. Again, this is something that's not usually something that's to worry about, but it could be. And again, it's not because large sample sizes are in principle bad. It's because large sample sizes just mess up the simplistic mathematics we're doing. And you'd have to use more complicated mathematics and hypergeometric functions and stuff like that. And we don't want to do that. Okay, and then the success-failure condition. This really is a big deal. And it is easy to mess up. Okay, and this says your sample size needs to be big enough. Okay, so NP and NQ have to be big enough. Okay, so N is 900, and our expected, if it's just perfectly representative of the national pool, out of 900 students, guess what? We should have 70%, or 630 people succeeding in moving on to sophomore year. Okay, that's way bigger than 10. Okay. And NQ is 900 times 0.30 is 270. That's still way bigger than 10. So we're easily satisfying the success failure condition. This is the one that really is the more interesting condition. It says sample size ought to be big, and especially if either P or Q is small. If it's something where it's very likely to happen or very unlikely to happen, then it's a bit more dodgy. It's harder for it to become accurately modeled by a normal. But this is fine here. Okay, so we've checked all that. Okay, and then the last thing is state the parameters and the sampling distribution model. Okay, so we've got a normal model with the mean, oops, wrong one, with the mean equal to the mean of the proportion that we expect is just going to be the same proportion as we got here, okay, just 0.70. If the whole pool is 70%, then the mean of any sample should be exactly representative of that, on average, okay? And then the sigma is much less obvious, but that's comes from the binomial calculations in the last chapter, that if you just repeat something that happens 70% of the time, and you repeat it 900 times, and you say, what's the spread in how many times that's going to happen? And then you divide it by the 900 to get a proportion, we get this wonderfully simple formula. It's just the square root of PQ over N. Okay? And that's the square root of 0.70 times 0.30 over 900. Okay? And we'll evaluate that. And so it's about 1.5. It's 10 to the minus 2, so that means percent. 1.53% basically. Well, let's keep the accuracy. 1.5275%. Okay. So we've got a normal model in terms of the percentage with mean 70%. Let's go ahead and translate that into 70%. Okay. And the standard deviation 1.5275%. Notice that's pretty small, okay, compared to the 70%. Okay, so let's draw a picture. Okay, I had the computer draw a accurate normal model picture for me, mainly because it's hard to freehand on this thing. So here it is, 0 to 100. Here's the picture. It's a very sharp normal model because the standard deviation is pretty small. It's just a few percent. The fact is, 900 is a pretty big sample size. Notice how how much bigger than 10 we were. We were way into the region where the normal is very accurate, and then it becomes something where the normal is actually very sharp. And so it's mean at 70, and the standard deviation is just a few percent. If we zoom in a little bit, it looks more like our normal model picture. But you can see that the standard deviation, like this is 70 to 72.5. Already we're way below kind of the mid-shoulder place where we would expect the plus or minus 1 standard deviation. So plus or minus 1 standard deviation is like this much. Okay, so that means that 68%. I don't have a good way to draw the vertical lines and stuff like that. But in here in this region, we'd expect about 68% of the schools to follow. Okay, so let's see. Let me sync these guys up again. Okay, so let's use the 68, 95, 99.7% rule. Okay, so we expect about 68% of these colleges to have a retention rate between so 70. Well, let me put it in math mode. 70 minus, what was it? 1.5. I'm going to drop some accuracy. 1.5. Actually, since I'm just saying about, I'm going to just take it down to 1.5%. Equals, so 68.5% and 71.5%. And 95% of the colleges to have a retention rate of between, so now we go out 2 standard deviations. Let's put it in math mode, just make it prettier. 67% to 73%. And the overwhelming majority of them, 99.7% of the colleges to have rates in between 65.5%. This is 3 standard deviations, 3 sigma, to 74.5%. Okay. Now, if we had looked at smaller sample sizes, in other words, smaller colleges, we wouldn't have such a good lock on the percentages. It's because it was a pretty large group of people. It's really narrowed down that variation in the percentage. The key is the 1 over square root of n here. That turns into a 1 over 30 when you square root it, and that's dropping down the original sort of sigma, the core sigma of square root PQ, to a very manageable size. Okay, so this is the predictability of statistics in a nutshell. When you sample with large sample sizes, you should get more probability, less variation, more predictability is what I mean. Okay, what about the tell stage, conclusion? Okay, interpret the results in context. Well, let's say for colleges of this size, if the assumptions are valid, we have good predictability of the retention rate. It will be very close to 70%. Okay. Another way to say it might be, if you then discover a college with 900 people in the freshman class that had a retention rate that was very different, then the assumptions must not be valid for that college. It's not really representative of the population. Okay. And that was really the big issue. The warning is that a college freshman class is not an SRS. It's not a simple random sample. Okay, there may be systematic factors making the retention rate different. The truth is, colleges differ very, very much from college to college. What their clientele is, what their expectations are, and you could get a very different result. Okay, so this is definitely oversimplified, but it's definitely a start as well.